Hey guys, welcome back. Sorry we got kind of cut off there. I thought I could fit that last little bit of info in before it timed out on me. Anyway, we were going over all these inflammatory chemicals that are going to cause all these symptoms of inflammation. If we kind of step back for a second, we can go over them in a little more detail. Those inflammatory chemicals are going to cause vessel diameter to do what? To go up. Capillary permeability to go up. This causes capillary blood flow and fluid loss to increase. That is going to be responsible for the heat, the redness, the swelling, and also the whole point of this is greater access for the important components of blood, the important immune components of blood, to get to the damaged area. We're going to get white blood cells there. We're going to get platelets there. We're going to get complement proteins, antibodies, all that good stuff. And of course, the swelling coupled with the pain leads to loss of function, which makes you less likely to utilize a particular damaged tissue, which is going to enhance healing. All right, what about fever? Well, in your hypothalamus, you have a thermostat, and that thermostat is going to regulate your body temperature. When you have an infection, when you have bacteria, viruses, infected cells, they're going to release chemicals called pyrogens. Pyrogens are also released by activated white blood cells, released by damaged tissue cells, and pyrogens reset the thermostat. They bump the thermostat up. So your body feels really cold at first. You're getting really cold. You're putting on a blanket. You're shivering. You're still cold because your body is trying to get you to this new set point. And a mild to moderate fever is generally a good thing. It's going to enhance your white blood cell function. It's going to decrease the function of your whatever microbe is invading you. It's going to let the liver and the spleen hide zinc and iron that bacteria would otherwise utilize for their own reproduction. So popping a Tylenol to reduce a fever is not always a good thing. I mean, obviously when a fever gets too high, that's bad. Temperatures that are too high can denature proteins. And denature brain proteins, you can die. And that's, of course, bad. Okay, that's it. We're done with innate stuff. Almost done. So close. So close. Explain to me why, back in the day, whether it was 700 years ago or 150 years ago, why would bloodletting be a natural, logical way to treat a fever? Okay, now we're done the innate immune system. So we can totally go on to the adaptive immune system. It is more systemic, it's more body-wide. Innate's more local. But that's not the cool part. The most cool, that's some horrible English right there. The most cool part of the adaptive immune system is it adapts. It lives up to its name. And I like the idea of improvement. It gets better at the killing. Second time around, whatever the infectious agent it's gonna get killed faster. It's gonna get killed deader than the first time. And in order to improve, you got to be able to remember. In order to remember, you got to be able to specifically recognize. So that specificity is a key here. Don't forget that. Now, here's an antigen. Antigen is our catch-all term for any foreign thing. An antigen is going to provoke an immune response. Notice how this antigen has all these different proteins on it that are actually getting different varieties of antibodies to respond to it. Notice how the antibody is specific for the shape of the antigen. And that is a crucial thing that lets the adaptive immune system rather, have specificity, have memory, and get better. Okay, first thing we got to deal with is a variety of cells known as antigen-presenting cells. And in this category, we're going to have macrophages, who we've met already, dendritic cells, who we've met already, and B lymphocytes, who we're familiar with. What these guys are going to do is they're going to engulf a antigen, a foreign thing. So here's my macrophage. It's sticking its pseudopods out. It is engulfing this foreign antigen. Now, upon engulfment, the engulfed antigen is in a phagosome. The phagosome fuses with the lysosome. The lysosome has digestive enzymes, which are going to chop up the pathogen, the antigen, whatever it is, into little pieces. Then here's the part that's interesting. The macrophage, whichever antigen presenting cell we're dealing with, is going to then take those pieces and display them on the surface. Basically saying, hey, I just killed this thing. This is what he looks like. Everybody go get him. And not really everybody go get him. In fact, the macrophage would only display this antigen to a specific helper T cell that had the right receptor on its surface that would match up with this. And then that helper T cell would enact an immune response, would direct an immune response to deal with that particular antigen. Oh, and by the way, these little purple rectangles, these proteins, these little purple rectangles, are known as MHC2 proteins. They're only found in antigen-presenting cells. They are the little display cases for the pieces of antigen that were engulfed and chopped up. Another image of the same thing. Here's our dendritic cell in this case. Here's our bacterium being engulfed in a phagosome. Phagosome goes, fuses with a lysosome, chop up the engulfed bacterium. Then we're going to take pieces of it, stick them on these MHC2 proteins embedded in the wall of the dendritic cell, where they can be displayed for a helper T cell. Not any old helper T cell, but the one with the correct appropriate receptor. Alright, so antigen presenting cells, they're one group of cells we got to deal with. And we're going to talk about lymphocytes. We have been already a little bit. Two main classes, of course, are T's and B's. Both are formed in the red bone marrow. We know that is where we do hemopoiesis. Now, both lymphocyte varieties, T's and B's, are made in the red bone marrow. The B's are not only made there, they mature there too. Better word for mature is immunocompetent. So B lymphocytes become immunocompetent in the bone marrow. Once they leave the bone marrow, they're immunocompetent, they're able to do their job. They're naive, they haven't done it yet. However, we've touched on this already, T lymphocytes do not mature. They do not undergo training in the bone marrow. They have to travel to the thymus, and we know this occurs in the infant and the fetus primarily. And the thymus is where T lymphocytes are going to mature, where they are going to become immunocompetent. And notice we're going to have two types, helper and killer cytotoxic. Another way of saying killer, helper and killer T lymphocytes. And of course, the T in T lymphocytes stands for thymus. It would be nice if the B in B lymphocytes stood for bone marrow, but it doesn't. It stands for something else. If you're really curious, ask me. I'll tell you. Okay. T lymphocytes. We know they're born in the red bone marrow. We know they travel to the thymus. There's the thymus of the fetus right there, big. Here's the thymus, chock full of T lymphocytes. This is where they mature. They become immunocompetent. They are able to respond to a specific antigen. So what the T lymphocytes have to acquire in this maturation process is receptors. Okay, not a whole variety of receptors. A T lymphocyte will generally have about 100,000 copies of a single receptor. By having a single type of receptor on its surface, that allows it to be specific for a certain antigen. And specificity breeds memory, which breeds improvement. So we got to the T lymphocytes have got to build these receptors whilst in the thymus. And in the thymus, we also do a check. We make sure the T cells are self-tolerant. What that means is we make sure they don't attack our own body proteins, our own body tissues. Any T lymphocyte that could, we want to cull from the herd. We want to select them out and kill them, not give them a chance to become part of our normal roaming population of T cells. Here we see the two types of T cells, helpers on the left, killers on the right. Helpers, by the way, coordinate your immune response. Killers kill infected cells, kill cancerous cells. Notice that on these guys, we've got TCRs, T cell receptors. And each of these guys have about 100,000 copies of the same receptor. And remember, having a single variety of receptor creates specificity, which creates memory, which creates improvement. All right, see ya next time.